Hello friends. So today we are going to solve questions from modern physics, and these questions are from the year 2017. It consists of both mains and advanced. So 3 questions are from main and 2 questions are from advanced. And from the year 2018, we are also going to solve 3 questions from the main and 2 questions from the advanced. So in totality, we are going to solve 10 questions. So the first question, it was asked in the 2017 main, and it states that sub-energy levels of a molecule are shown in the figure. The ratio of the wavelength R lambda 1 is to lambda 2 is given by. So we have to find out the ratio of lambda 1 and lambda 2, which is represented as R. And the energy levels are given to us. So we know the basic formula, which tells us that the energy level, or we can say difference in energy level, delta E will be equal to hc upon lambda. So we have two wavelengths, so we can modify this equation as per our requirement. So our first wavelength is lambda 1 rather. So we can say for lambda 1, delta E will be equal to minus E and minus of minus 2E, because the transition takes from this minus E to minus 2E, and this gives us, this will be equal to rather hc upon lambda 1. So from here we can say that our lambda 1 will be equal to hc upon E. Similarly, we can write for our lambda 2, and for lambda 2 the transition is from E to minus 4 by 3E. So this comes as minus E and minus of 4E divided by 3, and that will be equal to hc upon lambda 2. So this gives us that our lambda 2 will be equal to, this comes as 1, 3. So with this we will be getting as 3 hc upon E. So we got our lambda 2 as well as our lambda 1, and its ratio which is represented as R is equal to lambda 1 by lambda 2, and lambda 1 is our hc by E, and lambda 2 is our 3 hc by E. So hc by hc goes away, and we get this ratio is equal to 1 by 3. So option number C is correct. C is correct. Next question. It was also asked in 2017 main, and it states that a radioactive nucleus A with half-life T decays into a nucleus B. At T is equal to 0, there is no nucleus B. After some time T, the ratio of number of B to that of A is 0.3. Then T is given by. So we are given that we have a nucleus A and that decays into nucleus B, and we are given that our half-life of A, that is our T half, is given as capital T, and it is also stated that at start, so when T is equal to 0, B is amount of nuclei of B is equal to 0, and at time T is equal to T, we are given that the ratio of B to A, number of nuclei of B to A, is given as 0.3, and we have to find out this value of T. Okay, so this is the basic question that is given to us. So we start with A and use the decay law on A. Decay law for A, we can write that, and we can assume that at T is equal to 0, our A is having a concentration of nuclei is N0. Okay. So therefore at a certain time T, we can write this as Na of T is equal to, initial is N0 e raised to power minus lambda times T, and lambda we already know is our decay constant. Decay constant, and its value is equal to natural log of 2 divided by half-life, that is given as capital T. And here this Na T is the number of nuclei that are left after time T. And we can write, based on the decay law for A, we can write the equation for our B also. So you can say number of B nuclei and that is our NBT, and this NBT will be equal to initial of our A minus the remaining of our A. Okay. And we substitute value of Na of T, so from here we get that number of nuclei at a time T will be equal to N0, we can take common, so this becomes 1 minus e raised to power minus lambda T. And okay, now we are we are given the ratio of Na upon, ratio is given as, this is Nb and Na is 0.3. Therefore, we can write that ratio, which is our Nbt upon Nat, is given as 0.3. Therefore, we substitute, we get this as our N naught 1 minus E minus lambda T, and this is our N naught E raised to power minus lambda T. Here N naught and N naught cancel out, and we are left with 1 minus E raised to power minus lambda T and E raised to power minus lambda T. So we can solve it. Okay, and this small t is equal to capital T. One second, sorry, small t is equal to not capital T but decay constant in terms of capital T. Okay, that we already know. We can substitute that later on. So let me solve this equation now. So we are left with 1 minus E raised to power minus lambda T divided by E raised to power minus lambda T is equal to 0.3. So from here we can write that our, if we cross multiply by E raised to power minus lambda T, so this becomes 1 minus E raised to power minus lambda T is equal to 0.3 E raised to power minus lambda T. And this can be further written as, we get this from 1 is equal to E raised to power minus lambda T, we can take it common, and this becomes as one second. Okay, let me write it in other way. We can write this will be equal to 1 minus 1 upon E raised to power lambda T divided by 1 upon E raised to power lambda T is equal to 0.3. So this gives us that E raised to power lambda T minus 1 divided by E raised to power lambda T is equal to 0.3. Now we cross multiply it. We write this E raised to power lambda T minus 1 is equal to 0.3 E raised to power lambda T. And this can be further written as E raised to power lambda T is equal to 1 minus 0.3 is equal to 1, which gives us that E raised to power lambda T is equal to 1 upon 0.7, and this comes as approximately equal to 1.4286. And from here we can write that our lambda T is equal to natural log of 1.4286, and this can be approximately equal to natural log of 1.3, because if you check the options, it is always in terms of 1.3. Okay, so we can just approximate it, and this gives us that the value of T is equal to 1 upon lambda, and this comes as natural log of 1.3. Now we already know the relationship of t in terms of capital T. In terms of capital T means t half, and this can be written as our one second. Sorry, not once again. This the relationship is with respect to our lambda. Okay, so we substitute value of lambda. We need to find out this. So we get here t is equal to, and this becomes our natural log of 2 and divided by t, and here we have natural log of 1.3. Therefore we get our t is equal to capital T natural log of 1.3 divided by natural log of 2. So this is the value of t, and the option number A is correct. Option A is correct. Next question. It states that, one second, yeah, it's written correctly. It states that a particle A of mass m and initial velocity v collides with a particle B of mass m by 2 which is at rest. The collision is head-on and elastic. The ratio of de-Broglie wavelength lambda A to lambda B is. So we are given that we have a particle A of mass m and it moving with the velocity of v, and we have a particle B of mass m by 2 whose initial velocity, let us put that is our ub, is equal to 0. Okay, and they collide with each other, and then after collision, let us suppose our A of mass m is moving with the velocity of va, and we have our B, which is mass of m2, is moving a velocity of vb, and it is said that it is elastic and head-on. Okay. So let me write this as our u a is the initial velocity of A, which is equal to v. So we are given that, and after collision the wavelength is lambda A and this is for lambda B. So we are going to use conservation law. And you can say collision elastic, therefore we can write that final velocity of A and B for elastic collision final velocities of A and B. We can write that our VA is equal to m minus m by 2 divided by m plus m by 2 multiplied by v, and we have our, let us, vb will be equal to twice m and divided by m plus m by 2 multiplied by v. So if we solve them, we can get our VA will be equal to 1 by 3 times V, and we have our VB which will be equal to 4 by 3 times V. So we got the final velocities in terms of the velocity of A, basically initial velocity. Now we can just use our de-Broglie wavelength formula in terms of our momentum, which will be giving us a relationship with the velocity. So we can say de-Broglie wavelength that is of lambda is equal to h upon p, or we can say h upon mass into velocity. So for both A and B, we can write that our lambda A will be equal to h upon mass velocity of A, which can be written as substituting VA in terms of V. We get this as mv, and this is our 3h. Similarly, we can write our lambda B is equal to h upon mvb. This gives us, we have here m 4b 4v, and this is our 3h, and mass is our m by 2. Okay, let me put it m by 2, and this comes as 2 now. This will be 2. Okay. And we need to find out the ratio. So we get lambda A upon lambda B is equal to 3h upon mv, and this becomes 3h upon twice mv, and this in 3h mv cancels out, and we get this will be equal to 2. We have to find out lambda A to lambda B. So option number A is correct. A is correct. Next question. It was asked in the 2017 advance, and it states that a photoelectric material having work function phi naught is illuminated by light of wavelength lambda. Lambda is less than hc upon phi naught. The fastest photoelectron has a de-Broglie wavelength lambda d. A change in the wavelength of the incident light is given by delta lambda, results in a change delta d, lambda d in delta d, lambda d, sorry. Then the ratio of change in the de-Broglie wavelength to the original wavelength is proportional to. So it means we are changing the incident wavelength by delta lambda, and the corresponding change in the de-Broglie wavelength is given as delta lambda d. We have to find out their ratio. So we are given that the work function is phi naught, and we already know that the photon energy E it is given as hc upon lambda, and we can write that the kinetic energy of the photoelectron, kinetic energy of photoelectron, that is of K, will be equal to hc upon lambda minus phi naught. And we can also write the equation for de Broglie wavelength. De Broglie wavelength, which in this case specifically is mentioned at delta D, lambda D, sorry. So this will be equal to h upon 2mk and its square root. And we can further substitute value of k, giving us 2m hc upon lambda minus phi naught and its square root. We can modify this equation a little bit. We can write this as lambda t is equal to h, and this can be written as 2m hc upon lambda minus phi naught whole raised power minus 1 by 2. Now we are going to differentiate lambda d with respect to lambda. Differentiating lambda t with respect to lambda, and for that we can rewrite that our k was equal to hc upon lambda minus phi naught, and our lambda d was equal to h upon 2m and k square root. Therefore, from here we can write that our lambda d is proportional to k raised to power minus 1 by 2. Okay. So we are going to differentiate this equation. In terms of proportionality, it makes easy because rest of things is h and 2m are constant. So we get our derivative of lambda d, de Broglie wavelength with respect to lambda, will be equal to k, and this becomes our half. And please remember, this is in terms of proportionality, and this comes as minus k, this comes as minus 3 by 2, and we have dk by d lambda. And if we differentiate this equation with respect to lambda, we get dk by d lambda, and this will be equal to our hc, phi naught is our constant, and this will be coming equal to minus 1 upon lambda square. Okay. So we substitute and we get that our d lambda with respect to de Broglie wavelength is proportional to, we have this as minus 1 by 2 k minus 3 by 2 multiply by, here we have our hc, and this is minus 1 upon lambda square, and this can be further simplified as minus minus becomes plus. 1 second. Okay, Let us remove this 1 by 2 also, because that's not required. So this becomes as minus, and we get this. Well, let us keep it, we can just sort it out later on. This will be equal to our minus become plus, so hc upon 2 is equal to 1 upon lambda square, and this becomes 1 upon k 3 by 2. And we know that our relationship between k and lambda d we already know. Okay. So one second. Yeah. So this is a relationship between k and lambda d. So we substitute from k here. Let me write it here. We know that our lambda d is equal to h upon 2mk and square root. This gives us that value of k will be equal to h square, and we have this as 2m lambda d square. So we substitute value of k, and this gives us that our derivative of is proportional to hc upon 2, and this is our 1 upon lambda square, and we are going to get this as h square, and this is about 2m lambda d square, and whole raised power 3 by 2. Okay, and if I remember correctly, yeah, the answer is in terms of lambda and lambda d. We can just ignore all the terms, so we are going to ignore this entire ratio, and along with this h and this also 2m. So we get that in terms of proportionality, this will be coming as lambda d cube divided by lambda square. So this is our final answer, lambda d cube and square. So option D is correct. Next question. It was also asked in the 2017 advance, and it states that 131I is an isotope iodine that decays into isotope xenon with a half-life of 8 days. A small amount of serum labeled with 131I is injected into the blood of a person. The amount of 131I injected was 2.4 into 10 to the power 5 BQ. It is known that the injected serum will get distributed uniformly in the bloodstream in less than half an hour. After 11.5 hours, 2.5 ml blood is drawn from the person's blood and gives an activity of 115 BQ. The total amount of the blood in the person's body in liters is approximately. So here we are given that we have an isotope iodine, and that decays into xenon. We are given the half-life of 8 days is there. Okay, so we can say that half-life of iodine, that is our T half. It is given as 8 days, and its initial activity is also given to us. Initial activity is given to us as 2.4. So we can see initial activity that is our A naught is equal to 2.4 into 10 to the power 5, and total time elapsed is given as 11.5 hours. So we can write time elapsed that is value of small t is our 11.5 hours, which can be written as 11.5 divided by 24 days. And we are given that the sample which was taken out was our 2.5 ml, and its activity is said to be 115. So we can say that activity of two 0.5 ml sample after time t, after t, let us call this as A sample, which is given as 115. We will need to find out total volume, blood volume, that is in liters. Suppose that is V. So we start with activity decay formula. Decay formula, which gives us that our A is equal to our A naught e raised to power minus lambda t. Lambda is our decay constant, and its value formula we already know. Lambda, that is our decay constant, is equal to natural log of 2 divided by t half, which gives us 0.7 divided by 8 is equal to 0.0875 days inverse. And we can just write this ratio also, and this will be coming as 0.04, sorry, not 4792 days. Therefore, we can find that the fraction between A and A naught, so we can say the fraction of activity left fraction of activity left after time t, and that formula will be our A upon A naught is equal to e raised to power minus lambda t, and we already know these values. So we get e raised to power minus lambda is our 0.0875 times t is our 0.4792. This can be approximately written as e raised to power minus 0.0419, and we are given in the question that we can use that E of x is approximately equal to 1 plus x. Okay. So we can use that. So we can write e raised to power minus x is approximately equal to 1 minus x. Therefore, based on this, we get e raised to power minus 0.0419 is approximately equal to 1 minus 0.0419, giving us 0.9581. And we need to find out the activity after 11.5 hours. So we can write activity after 11.5 hours. This will be giving us A of t is approximately equal to A naught 0.9581, and A naught is also known to us, that is our 2.4 into 10 to the power 5. So we get our A of t is equal to 2.4 into 10 to the power 5 multiplied by 0.9581. So we get activity after time t is approximately equal to 2.3 into 10 to the power 5 BQ. And we are going to find out the total volume V. But this activity is with respect to 2.4. Sorry, not 2.4, but 1 second. Yeah, 2.5. Okay, so activity of 2.5 is given as 115, and because this is the only sample, it means that 2.5 milliliter of sample is giving an activity of 115. So if V is the total volume, then with respect to V, we can modify this equation in terms of V also. So we can write it as proportion in 2.5 ml. Proportion in 2.5 ml, because the activity that is given to us is given with respect to this particular sample. Okay. So we assume that our total blood is V milliliter. Therefore, we can write that our 2.5 divided by V multiplied by our A of t is equal to 115. And we know all these values. We are interested in V. So we can write this as our V will be equal to, this comes as our 2.5 multiplied by A of t, that is 2.3 into 10 to the power 5, and divide by 115. So this will be approximately equal to 5000 milliliters, or we can say that our volume V will be equal to 5 liters. Liters is approximately 5. Next question. It It was asked in the 2018 main, and it states that in series limit frequency of Lyman series is VL, then the series limit frequency for P-Fund series is. So here we can use just Rydberg formula directly and solve it. So you can say Rydberg formula, but Rydberg formula, the standard one is given in terms of our, you can say, wavelength lambda. This we can write in the terms of frequency. So Rydberg formula in terms of frequency will be equal to frequency nu is equal to R multiplied by C. C is the speed of light, and rest of the things will be same. And here our N1, this will be our lower energy level, and this lower energy level is fixed for each series, fixed for each series. And we have our N2, and N2 will be equal to infinity because we have to find it for our series limit frequency. Limit frequency. For the first one is given to us a Lyman. Therefore, we can write for Lyman series and we know that N1 is equal to 1 and our N2 will be our infinity. And in this case, the frequency is given as nu L. So we can write this as nu L will be equal to our RC 1 upon 1 square minus 0, giving is product of Rydberg constant multiplier speed of light. And similarly, we can write the equation for our P-Fund series. Here the N1 value is about 5 and our N2 limiting value is about infinity. So let us call this as frequency as Vp, nu P rather. So we can say nu P will be equal to our RC 1 upon 5 square minus 0. This gives us RC upon 25, and RC is nothing but our nu L. So we get this as nu L upon 25. Okay. So the answer will be option number A is correct. Next question. It was also asked in the 2018 mains, and it states that an electron from various excited state of hydrogen atom emit radiation to come to the ground state. Let lambda n, lambda g be the de-Broglie wavelength of the electron in the nth state and the ground state respectively. If delta n be the wavelength of the emitted photon in the transition from nth state to the ground state for large n, we have to find out the relationship between this lambda n as well as lambda a and b are given as to be constant. So we are having two de-Broglie wavelength respectively for nth state and for the ground state. Okay. So we can write this in the formation of our energy. And we can say that the standard formula for energy is equal to our okay. So we can say our kinetic energy is given as p square upon 2m, and we already know the equation for a momentum. Then we can write this will be equal to our h square 2m lambda square. Okay. And we can divide this equation in terms of our energy, kinetic energy. Let us suppose this is represented as our K, and we know that our energy is equal to our minus of K. So this comes as minus h square upon 2m lambda square. So we can write this equation in terms of our nth state as well as ground state. Okay. So you can say that for nth state we get our E of n is equal to minus h square upon 2m and delta lambda n upon square. And for ground state that our E of G is equal to minus h square 2m lambda g square. Now we can find out their difference. So we can write that our En minus Eg will be equal to, this will be our minus h square and two m lambda n square minus of minus h square upon 2m lambda g square. And we can take common, so we get from here h square upon 2m, and this will be 1 upon lambda g square minus 1 upon our lambda n square. And this difference is, let us suppose, represent as our delta of E, and this delta of E can be written as our hc upon, here delta is represented as A, reverse A, so let me write it. This is the representation of delta in this particular case, so accordingly we modify it, and this we can write as our delta of n. And now we can just solve it. We can take our LCM, and square goes with this h, and we get this as our C upon delta n is equal to h upon 2m. This will be equal to our lambda g square lambda n square, and we are left with our lambda n square minus lambda g square. And we can write from here that our delta n will be equal to 2mc upon h, and lambda g square, lambda n square, and we have lambda n square minus lambda g square. And we are going to solve this particular part, and we can write, if we, this can be written as is equal to 2mc upon h, and we can take our lambda n square, okay, taking lambda n square common, so we get this as lambda g square, and we have this as 1 minus lambda g square upon lambda n square. This can be further written as 2mc lambda g square upon h, and this is equal to 1 minus lambda g square lambda n square and whole raised power minus 1. And we can expand it binomially, and this will be giving us 2mc lambda g square h, and this becomes 1 plus lambda g square and lambda n square. We multiply inside, this will be coming as 2mch multiplied by lambda g square plus, we have here 2mch and lambda g4 and lambda n square. Okay, everything is in terms of lambda n. So let me club this part also here, lambda g square. So we can write this is equal to a plus b times lambda n square, okay. And this would be g4, and we can say this is a entire term is a constant represented as a, and this is a second constant which is represented as b. So therefore delta n is given as a plus b divided by lambda n square. A plus b divided by lambda n square. Option B is correct. Correct. Next question. It was also asked in 2018 mains, and it states that the reading of a meter of a silicon diode in the given circuit is given to us. We have a 3 voltage source and diode which is silicon, and we have to remember that it's 0.7 is, and this is about 200 ohm, and we have to find out value of current, that is I. And so this 0.7, let us suppose this is our V diode, So the voltage drop across the diode silicon is 0.7. So we have to find out the current. So we can just use our KVL, and or we can just use equivalent voltage source also. So this is a voltage source of 3 and we have a voltage source of 0.7, and this 0.7 will be opposite to this 3. So we are going to get 3 minus 0.7. Okay. Or we can write this, let be BV. So we can say current I will be equal to V minus V diode divided by total resistance R. This will be equal to our 3 minus 0.7 divided by 200 ohm, giving us 11.5 milliampere. Option D is correct. Next question. It was asked in 2008 advance, and it states that consider a hydrogen-like ionized atom with atomic number Z with a single electron. In the emission spectrum of this atom, the photon emitted is in N2 to N is equal to 1. Transition has energy 74.8 electron volt higher than the photon emitted in N is equal to 3 to N to 2 transition. The ionization energy of the hydrogen atom is 13.6 electron volt. The value of Z is. So we can just use the standard equation for energy level for nth energy level for hydrogen atom and start from there, because we are given two energy levels, N to 2 transition and N to 3, 3 to 2 transition. So we can say that nth energy level which is our E of N is equal to minus 13.6 Z square upon N square electron volt, and the first transition is straight from N 2 to 1. Therefore we can say transition from 2 to 1, and let us call this energy as E to 1 will be equal to energy at level 2 minus energy at level 1, which will equal to minus 13.6, and our Z square divided by 4 minus minus of 13.6 Z square divided by 1, and this comes as our, we can take 13.6 Z square as common. This will be our 1 minus 1 by 4, which giving us 3 by 4. Therefore and second transition is from 3 to 2. So we can write that our E32 will be equal to our E3 minus E2, giving us minus 13.6 Z square upon 9 minus of minus 13.6 Z square upon 4. We can take once again 13.6 as common, and this will be equal to 1 by 4 minus 1 upon 9. This comes as 36 and 5 upon 36. And we are given that the transition energy is higher by amount of 74.8 electron volt. So we can write that our E21 minus E32 will be equal to 70.4 electron volt. So we simply substitute their values. We get this as, we can take 13.6 as common from both. We get this as 13.6 z square, and we are left with this as 3 by 4 minus 5 by 36 is equal to 74.8, and 36 will be a LCM, so this becomes as 27 minus 5, and 27 minus 5 will be equal to our 22 upon 36. So we can say that we need to find out our z square. So we can say our z square will be equal to 74.8 divided by 13.6 multiplied by LCM will be our 36, and this will be equal to 27 minus 5, 22, and this will be approximately coming equal to 9, or we can say our z is equal to 3. So value of z is equal to 3. Next question. It was also asked in 2018 advance, and it states that in a photoelectric experiment, a parallel beam of monochromatic light with power 200 watt is incident on a perfectly absorbing cathode of work function 6.25 electron volt. The frequency of light is just above the threshold frequency, so the photoelectrons are emitted with negligible kinetic energy. Assume that the photoelectron emission efficiency is 100%. A potential difference of 500 volt is applied between the cathode and the anode. All the emitted electrons are incident normally on the anode and are absorbed. The anode experiences a force of F is equal to N into 10 to the power minus 4 Newton due to the impact of electron. The value of N is. So here we have to remember that kinetic energy, the electrons that are emitted are having negligible kinetic energy. So first of all, we are given that the power of incident light suppose that is P, it is given as 200 watt. Work function is also given to us. Work function that is above phi, it is given to us as 6.25 electron volt, and it says that the emission efficiency is 100%, which basically we can interpret it as that one electron will be proportional to one photon. We are given that emission efficiency is our 100%, so we can write it as 1 electron per photon. And another important part is that the kinetic energy is approximately equal to 0, negligible kinetic energy. So you can say electrons emitted with negligible kinetic energy. So first of all, okay, and another thing that is mentioned here, that where it is, yeah, the frequency of light is just above the threshold frequency. Okay, so because of this, you can say that energy per photon is approximately equal to work function. So in the first part, we are going to calculate energy per photon. Energy per photon. And we are mentioned that our frequency is just above threshold. Therefore, from here we can derive a conclusion that energy per photon is equal to our work function. Or indirectly also, the kinetic energy is approximately negligible. So from there we can also derive this conclusion. Therefore, we can write that our energy associated with photon is equal to our work function, which is our 6.25 electron volt, and we convert into joules, that is 1.6 into 10 to the power minus 19 is equal to, this comes as our 1 into 10 to the power minus 18 joules. Now we can find out number of photons per second. Number of photons per second, and this will be P upon, sorry, P is the power, capital P upon energy of the photon, which is equal to our 200 and 10 to the power minus 18, giving us 2 into 10 to the power 20, and efficiency is given as 100%. Therefore, we can say that same number of electrons are emitted per second, or we can say number of electrons per second will be also equal to 2 into 10 to the power 20. Okay, because we just wrote it here, 1 electron is per photon. Now we can just use the kinetic energy and find the final velocity of each electron. Final velocity of each electron, potential difference is given as V. Therefore, we can say kinetic energy is equal to E times V, which is about 1.6 into 10 to the power minus 19, and the potential is our 500, this comes as 8 into 10 to the power minus 17 joules. This is nothing but our half mv square. So we can say our half mv square is equal to 8 into 10 to the power minus 17. This gives us that the velocity v will be equal to 2 into 8 into 10 to the power minus 17, and mass is our 9 into 10 to the power minus 31 and its square root. So this comes as approximately as 1.33 into 10 to the power 7 meter per second. And from here we can find out the momentum of each electron. Momentum of each electron, that is our P is equal to our, this is our mass of electron. Mass of electron multiplied by velocity v, which will be equal to our 9 into 10 to the power minus 31 into 1.33 into 10 to the power 7. So we get our momentum P will be equal to 1.2 into 10 to the power minus 23. And now we come to the force part. We already know momentum, therefore we can say that the force on anode that is of F will be equal to n multiplied by the momentum. That is force in the rate of change of momentum or number of electrons per second multiplied by electrons per second. Okay. Let me write it. Force on the node is our rate of change of momentum, or we can also write it as number of electrons per second multiplied by momentum per electron. Therefore, force represented as F, number of electrons per second is capital N, and momentum per electron we just found is our P. And so we know the value of force is n into 10 to the power 4. Okay. So this comes as our equal to 2 into 10 to the power 20 multiplied by 1.2 into 10 to the power minus 23. And this comes as our 2.4 into 10 to the power minus 3. And the given formula for 4 is our force is n into 10 to the power minus 4. So based on this, we can say that our n into 10 to the power minus 4 is equal to 2.4 into 10 to the power minus 3. And value of n is equal to 2.4 into 10 to the power minus 3 10 to the power minus 4. This gives us that the value of n is equal to 24. Is our 24. So this completes all the 10 questions from 2017 mains as well as 2018 mains as well as advanced. So this completes all the 10 questions. Thank you.